I'm not chopping these problems, I'm just putting the whole file online. So okay, we'll do one of these problems. I'll let you pick one of these. This will just be too long. I mean, so this problem is like this problem here, there, and there. So this is like 3 of these problems. And you can see that this and this, all these 3 are similar. This being the simplest because this force has only one component, X component. So pick between these 2 guys. Okay, I guess this is easier because the angles are the same. So we'll do this one. Okay. All right, so the idea is the following. You can look at it several ways, but let's say there's a knot here. Now what do you want the knot to be at rest? Okay, so what are the 3 forces acting on the knot? This tension, and that tension. Yep. And you want the knot to be at rest. Yep. So we're doing part C. So mg, so the tension in this string T3 equal to mg. This is 45 degrees, this is 60 degrees. Okay. All right, and this should always be in the background. You should draw your x and y axes. Okay. All right. So there is the knot, and the 3 forces on the knot are T1, T2, and T3. Okay. And what is it that you want? You don't want the knot to move, so okay. How many equations is this? I'm sorry? Well, so it's 3 generally, but these are forces in 2 dimensions, so that's 2 equations, x and y components. Okay? So T1x plus T2x plus T3x should be 0, and T1y plus T2y plus T3y equal to 0. Okay. All right, now what we'll do is we'll write these forces in component form. So T3 we already know is just in T3 is minus T3 is minus mgj. T1 is, it has a negative x component and a positive y component. Yeah. So T1 is minus T1 cosine 60i, and T1 is the magnitude, plus T1 sine 60j. T2 similarly is T2 cosine 45i plus T2 sine 45j. Okay. T1 was that, T2 is, there's the x component and there's the y component. Everybody agree? Okay. So what is it that we want? So let's put all of that in there. T3x is 0, so T1 and T1x plus T2x should be 0. So what we have is from the x components minus T1 cosine 60 plus T2 cosine 45 equal to 0. So what this gives you is T1 in terms of T2. So T1 is cosine 45 divided by cosine 60 times T2. Okay. What I did was I brought this over there and then divided that by cosine 60. Okay. Okay, so what we have found is T1 is 40% greater than T2. Okay? And that makes sense. See, T1 is more vertical, and so it's supporting the greater load. Okay? All right. Now we want to find this in terms of, so let's look at the y components. Now the y components are this y component and this y component is balancing that y component. Okay? So T1 sine 60 plus T2 sine 45 minus mg equal to 0. Okay. And let me write that. All right, so we have the answers now, and let's see what did we achieve. Okay, so here's what we achieved. Okay, you wanted to hang the sign, mg. So what you could do is, you could just take a straight cable and hang it there. T3, and the tension would be mg. Why did you go to this trouble?
It's less than mg for both.
Very good. So these two guys are weaker. See, this guy is 73% of mg. That's a cheap cable. This is an even cheaper cable. That's what you achieve. Okay? Did you guys understand that? This is an expensive cable. All right, any questions on this? You understand? Okay. All right. Yep. I'm sorry?
Can I check the last thought?
All right, sure.
Thank you.
Mm-hmm. All right. So this says a uniform plank rests on a level surface as shown below. The plank, whenever there's a uniform plank, what they're meaning is the center of mass is at the geometric center, okay, and the center of gravity is there. Okay, so that's where the weight of this thing acts. The plank has a mass of 30 kgs and is 6 meters long. How much mass can be placed on its right end before it tips? Okay, so the question is, how much mass can you place there before it starts tipping? Okay, so the problem is the following. So you put a mass there, and this is the mass of the plank that is acting like that. Okay, so this is the pivot point. This mass is trying to tip this guy about that point, and this guy is counterbalancing it. Okay, so this is a clockwise torque, and this force is providing a counterclockwise torque. And we're calculating the torque about this point. Okay. So what distance is this? Very good. This is the center of gravity. That's at 3 meters, so that distance is 1.2 meters. Okay. Okay. All right, so now we have the moment arms for each of these. Okay, so, and again, what is it that you want? You don't want this to rotate. So right now all you need is this equation. The sum of the torques need to be 0. And this torque is a clockwise torque. Clockwise torques are taken to be negative. Okay, so the z-axis is into and out of the paper, and this guy, so r cross, this would be r. Here's the vector notation r. So if you extend this r cross force F, the torque is going into the plane of the paper, okay? And that's taken to be negative. All right. So minus mg times 1.8 meters plus mg times 1.2 meters. Okay. So this torque is going into the plane, this torque is going into the plane, this torque is coming out of the plane, and that's the positive. Equal to 0. So 2/3 of the weight of the plank. Okay. What if you wanted a greater mass to be balanced? What would you have to do? I'm sorry? Very good. Either that or make the plank heavier. Okay. So, all right. So, That's what you do. Okay, so we'll do this one. It's a little more involved. All right, so this problem says the uniform boom shown below weighs 700 newtons. Okay, there is the boom, and that's weighs 700 newtons, which is roughly the weight of one of us. Okay? And the object hanging from its right end is 400 pounds, 400 newtons. Okay. So the boom is supported by a light cable and by a hinge at the wall. Calculate the tension in the cable and the force on the hinge and the boom. You've seen signs like this. So for instance, if you want to hang a heavy sign like that, you would have to calculate the tension in the cable and all that kind of stuff. Okay, so calculate the tension in the cable and the force on the hinge and the boom. All right, so there's the tension, there's that. And whenever they say a uniform boom, what they're trying to say is, what are they trying to say when they say the uniform boom? Yeah, center of gravity is at the center. Okay, that's where the weight of the boom acts. Okay? So that's what they're trying to say. Okay? So let's say the length of the boom is that mg, which is 700 newtons. All right. Calculate the tension in the cable and the force on the hinge and the boom. Okay. Calculate the tension and the force on the hinge. Okay, force off the hinge on the boom. So let's say that's the force of the hinge. Okay. So here's what's happening. This cable is pushing the boom into the wall, and it's pushing into the hinge, and this is the reaction force of the hinge on the boom. Okay. What we are interested in is all the forces acting on the boom, because the boom is at rest, hopefully. Well, you want the boom to be at rest. So we'll look at all the forces on the boom, and then we will apply these two equations to all these forces. Yeah. All the forces should add up to 0, and the torques of these forces should add up to 0. Okay? All right. So actually, I'll name this reaction force. I don't want a subscript because, okay. And again, we always draw our x and y axis like that. All right, so T, the tension is minus T cosine 45 I plus T sine 45 J. The weight of the boom is minus 700 J. This load is minus 400 J. R is Rx I plus Ry. We don't know the x and y component, and we'll calculate that. Okay. So let's add up all the x components of the forces. X component is minus this pen always drops the Bluetooth connection. Why does it happen? Does anybody know? Every once in a while it'll drop. And then if I go to the next page, it picks it up. It's the strangest thing, yep. I'm sorry? Oh, slower. Okay, yep, yep. All right. So what we're doing is, oops, we are making sure that the sum of these forces on the boom is 0. Okay? Because we don't want the boom to move. The center of mass of the boom is not moving. Okay? So we'll add the x component. These are the 4 forces acting on it. The x components of these forces should add up to 0. That's what we're doing. So minus t cosine 45. These two guys have no x component, plus rx equal to 0. Okay, so we have the reaction. The x component of that is equal to the x component of that. Yep. Now let's do the y component. The y component of this plus the y component of that is balancing these two forces. Yep. You guys understanding this?
Can you go back to the last one? Oh, that's right. Okay, thank you.
Mm-hmm. The y components, okay, this y component and that y component minus these two guys, okay. So t sine 45 plus ry minus 700 minus 400 equal to 0. T sine 45 plus ry minus 700 minus 400 equal to 0. Notice what we have. We have the x component of this reaction force in terms of the magnitude of T. We have the y component in terms of the magnitude of T. All right. So we've used up this equation. All we have is left one more equation. And we seem to have 3 unknowns, Rx, T, and Ry. And we have one equation left. Sounds like we're on a dead end. We run into a problem. So here's, go ahead. You guys understand the problem? So here's where that trick comes in. Now we'll calculate the torques about this point. That will eliminate this force. Okay, this guy will have no torque. Only this guy will have torque. So then we'll get an equation that involves only T. We'll solve for T and then solve for Rx and Ry. Okay? All right, so we will calculate the torques about this point. Okay, so this did you guys understand that? So that's okay. So calculate the torques about this point. Okay, this guy has a clockwise torque, which is negative. The moment arm is that. That is the moment arm. What is this length equal to? Can somebody tell me?
R cosine 20.
No, this length. That length is L. That length is L by 2. L by 2 cosine 20. Right? And this length is L by L cosine 20. Okay. So these guys are providing clockwise torque. What is providing the counterclockwise torque? The tension is providing the counterclockwise torque. Okay, now calculating the moment arm is difficult. This moment arm is difficult. So what we do is, well, we are smart. We can break this up into x and y component. And the moment arm of this, that is easy to calculate. That moment arm is L sine 20. And the moment arm for this guy is the same as this, which is L cosine 20. Okay? You guys understand? I see a few blank looks. What is the moment arm? The moment arm is the perpendicular distance from the line of action of the force to the axis of to the point about which you're calculating the torque. That's the moment arm. Okay. So if you extend this x component, that's the moment arm, which is equal to that distance. For this force, the moment arm is that distance. Okay? Yes, my friend. Go ahead. So you understand it 100%? No. Well, then ask a question. What is it that you do not understand?
I guess we like the,
Hmm?
the outside 20 comes from cosine 20.
Oh, okay. All right. So let me draw another diagram. L sine 20. Okay. So what we have done is we've broken the tension into its x and y component. So we replace this by that. Okay. This for this force. So this guy is t cosine 45. This is t sine 45. So essentially you removed this force and replaced it by these two forces. Okay. Now the torque for this guy is, there's the force, and the moment arm is this distance. Okay. That distance is equal to that distance. That is L, there's 20, and so this is L sine 20. Okay. So here's the triangle. This is L sine, this is L, the hypotenuse is L sine 20, L cosine 20. Okay. All right, again, this is a clockwise torque. This force is providing a clockwise torque. This force is providing a counterclockwise torque. This force is providing a counterclockwise torque. Okay. When I say counterclockwise torque, it's rotating this beam counterclockwise about that point. Okay. All right. All right, so now we are going to apply this equation, and we are going to calculate all the torques about this point. Why are we calculating the torque about that point? Why are we calculating the torque about that point? A soda to whoever answers it correctly.
Oh, but like a negative forces are being applied to like the plank from the pump.
So the torque will be zero at that point,
For what?
because you have the x-axis right there.
So, okay, the reason we're applying it about this point is we don't know R. And so we don't want to calculate R. To eliminate R, we calculate the torque about that point. Whatever force you don't know and you want to eliminate from your equations, you calculate the torque about that point.
How exactly will, I mean, I'm sure we'll see it in a second, but how, I think it just didn't click from the first time you said it, how will R be eliminated or found?
Okay, so what is the moment arm for R? The moment arm is
All over 2 cosine
No, so the moment arm for this guy, that is the axis of rotation. The moment arm is from the line of action, the distance from the line of action to the axis of rotation. This guy is passing through the axis of rotation. Moment arm is 0. And the torque is 0. All right, so let me go back. Okay, so let's do a simpler thing. So let's say we'll do here's a force. And you're calculating the torque about this point. R perpendicular. The torque of this force about that point is RF times this distance. Okay? So the torque is F times R perpendicular. And since this was a clockwise torque, it's a negative torque. Okay? So let's call this F1.
So because R is on the actual point of rotation, it's not creating torque. It's not
There you go, my friend. That's why we don't put door handles on hinges. You could never open the door.
I understand now, thank you.
Yep, even if you were Superman. You could pull the door out of the hinges. Okay? Did you guys understand that? All right. All right, so now we're going to calculate this. So I'm going to write one term at a time. You know how to calculate the torque. The torque is, again, if the force is like this, and you're calculating the torque about this point, again, I need more space. So what is the moment arm? The moment arm is you extend the line of force, and this R perp is the moment arm. Okay? So this is the line of action of the force, and the perpendicular distance to the point about which you're calculating the torque, that's the moment arm. And the torque is force times the moment arm. This is called the moment arm. You'll come across this. And is this torque positive or negative?
Positive.
Positive. It's making this force is making this object rotate counterclockwise about this point. Okay, so now let me confuse the heck out of you guys. What if I calculated the torque of this force about that point? Would it be positive or negative? So for some reason, let's say, you can think of this, okay, so maybe you want something physical. So let's say there's a stake there, and we've attached this object by a rope to the stake. And now I've applied a force at this point. So I'm calculating the torque. Yes, so then it would be negative, okay? So if you calculated the torque of this force about that point, it would be negative, okay? Any point west of this would be positive. Any point northeast of that would be negative, okay? So do you guys understand this? So what we are saying is the sign of the torque depends on what point you're calculating the torque for, torque about, okay? Don't worry about it. I'm throwing a lot of terms at you. Go home and think about it, and yeah, you'll be surprised. You will understand it. Okay. Okay. Some of the torques. How many forces are there? Let's go see. How many torques are we? How many terms are we getting? One for this guy. One for this guy. Another one for this guy. One for this guy. So we'll have 4 terms in our equations. We have 4 torques. This guy will rotate this object clockwise about this point. This guy will rotate this object clockwise about that point. This guy will rotate the boom counterclockwise. This guy will rotate the boom counterclockwise. So those will be positive torques. this will be negative 2. Okay. Make sure you understand this. Once you understand this, all the other problems will be easy. Okay. That's the point of hard problems. If you're able to go on a 20-mile hike, a 5-mile hike is nothing. That's the idea. Right? Okay. Evelyn is getting bored. You're just sleepy? All right. All right. So, the torque of this guy, T cosine 45, there's the moment arm. Okay? So, T cosine 45, there's the moment arm, which is equal to that distance. Okay? And that's a positive torque. So, T cosine 45, L sine 20 was the moment arm. All right. What is the torque due to this force? Can somebody help me out? T sine 45, and the moment arm is that. L cosine 20. Okay? And is it positive or negative?
Positive.
Positive. Very good. All right. Now we'll calculate the torque of this guy, the 400 newtons. The moment arm is that. Okay. Who's got it?
400 times L cosine, L sine 20.
There's the moment arm, L cosine 20. And is there anything you're missing? Negative 400. All right.
And then minus 700 L over 2.
Very good. Very good. And notice they didn't give the L in the problem. Here's why they didn't give the L in the problem. Yep. And here's the beauty of this. This equation you could write only in terms of T. And now you can solve for T. Once you have T, you can solve for Rx and Ry. And that was the whole point of picking that point as the point about which to calculate the torques. Okay? All right. Again, go home and review this problem. It's not going to be on the exam, but you got to understand it, you know. I'm not sure it's more like, okay. All right, so let me So tension in the cable is 783 newtons. Okay. So again, so this was a profitable endeavor. See, 700 newtons plus 400 newtons is 1100 newtons. The cable is only 770 newtons. Okay? Yeah. And now you can solve for Rx and Ry. Okay, so Rx is T cosine 45. All right, so there is Rx and Ry. So R is 553.7 I plus 546.3 J. Newtons, of course. Notice the X and Y components are almost equal to each other. So this guy is at almost 45 degrees. It's not along the boom, which is at 20 degrees. Okay. All right, guys.